we're going to be talking about what we call systems of equations or systems of inequalities, and we're also going to be looking at their solutions. So we're going to start by determining if a given point is a solution, or given a picture, can we determine the solution? And then we'll move into more algebraic methods and actually using equations and solving methods to determine the solutions. So first thing we have to point out is a little bit of vocab. A system of equations is two or more equations represented together, and a system of linear inequalities is two or more inequalities together. So remember the difference between an equation and an inequality is an equation has an equal sign, and an inequality has less than, greater than, less than or equal to, or greater than or equal to. When we talk about the solution of a system of linear equations, we are talking about the ordered pair or the point that all equations pass through. So the point that if we have two equations where they intersect, or if we have three equations, the point where all three equations intersect. And if all the equations intersect in this point or meet at this point, the point makes all the equations true. A solution to a system of linear inequalities is slightly different. Inequalities differ from equations because inequalities have shading where equations don't. If you think back to a one-dimensional system, for example, x is greater than 2, I shade everything above the 2. So when I look at a graph of a system of linear inequalities, my solutions are going to be all the ordered pairs that fall in the overlapping regions, so that where the shading for each line overlaps. And we're going to look at what that means, and also makes both inequalities true. So I'm going to look at two parts to this video, so please make sure you do watch two parts since they're different. The first part is going to be naming solutions given a picture. So again, with equations, we'll name the point of intersection, and with inequalities, we'll name any point inside the overlapping region, so the overlapping shading. So on this first example, and I do just have one example of each, I know the graph is a little bit small, so it's kind of hard to see, but all I'm going to do is name the point where they intersect. And we always name, see if I can blow this up a little bit, we always name a point as x comma y. So I first go ahead and ask myself, how far did I move right or left? What's my x value? And it looks like I move over 1, 2, 3, and then I move up or down, in this case down, 1, 2. So I'm going to go ahead and name my point, shrink this back down to normal size, and I'm going to go ahead and name my point 3, because I moved over 3, negative 2, and I went down negative 2. On the next example, now I have inequalities. Again, I know they're inequalities because of the shading. And I notice that all the solutions to this first inequality here, y is less than or equal to negative 2, was shaded in red. All the solutions to this second inequality here, y is greater than negative 3x plus 5, were shaded in blue. Well, what happens when you put blue and red together? You make purple. So this is my overlapping region. So according to my notes here, if I want to name 3 solutions, all I need to do is name 3 points inside of that purple region. So I can pick any 3 points I want. So let's say I pick this point and name it. Let's say I pick this point and name it. And let's say I pick this point and name it. So my first solution is, it looks like I go over from the origin over 4 and up 1. So I'm going to go ahead and say that's 4, 1. And my next point right here looks like, again, I go over 4, but now I go down 1, 2, 3. So I also have 4, negative 3. And finding one more, or naming my last one, I already found it. I go over 6, down 1. So I'm going to go ahead and say 6, negative 1. Of course, there are lots of different points I could have chosen, but I was only asked to name 3. Now let's go ahead and look at the second part. So that is naming the solutions from a picture. Now if we are given the point and an equation without the picture, could we determine if it is in fact a solution? Well, if you remember from up above, I pointed out that if it is a solution, it makes the equations true. So what we're going to do is we're going to plug the point in and see if it's a true statement. So on the first example, I have an A and a B. So on letter A, I'm going to go ahead and plug the point 2, 1 in, where 2 is 1 and x is y, or 2 is x and 1 is y. So into the first equation here I get y, so 1 equals 2 times 2 minus 3. Well, that means 1 equals 4 minus 3, so 1 equals 1. Well, yeah, that's a true statement. But it has to work for all of them, so it also has to work for my second equation. So So I'm going to go ahead and do the same thing for my second equation, plugging 2 in for x and 1 in for y. Simplifying, I get 1 equals 1, which is also a true statement. So when asked if this is a solution to the system, I'm going to go ahead and say yes, a solution. I'm going to do the same thing on part B. Again, I'm going to plug x and y into my equations, and I will have y equals, I wanted to plug 1 in for y, so I'll have 1 equals -1/2 times 2 plus 2. Well, I know with fractions I can reduce first, so I'm going to say 2 and 2 are both reduced by 2, giving me 1 equals -1 plus 2. So 1 equals 1. So again, it works. Plugging into, again, the second equation, I get 2 plus 3 times 2 plus 1 equals 5. Well, that gives me 2 plus 5 plus 1. Well, that gives me 8 equals 5. Well, I know that that's not true, so it did not work for both of them. And to be a solution to the entire system, it has to work for both. So I would say no, not a solution. Determining if a point is a solution to a system of inequalities works the same way. I'm going to go ahead and again plug my point in. And so I'll have, again, x comma y. So I'll have 2 is greater than 2 times 3 minus 5. So 2 is greater than 6 minus 5. 2 is greater than 1. That sounds true to me. Plugging into my second equation as well. 3 times 3 plus 4 times 2 is less than 12. So 9 plus 8 is less than 12, which means that 17 is less than 12. Well, I know that that is not true, so that one did not work. So no, 3, 2 is not a solution to that system of inequalities. Doing the same for part B, again, I'm going to plug in 3 for x, 2 for y. So I'll get 2 plus 2 is greater than 3. Well, that means 4 is greater than 3. Yes, that checks out. But I also have to check the second inequality. So 2 is 2 is less than or equal to -1/3 times 3 plus 3. Again, using rules for multiplying fractions, I reduce my 3's, and I get 2 is less than or equal to -1 plus 3. So 2 is less than or equal to 2, and because I can either have this side be less or equal, it is satisfying the part where it says or equal, so I'm going to go ahead and say that works. So yes, the point is a solution. So once again, bring your notes with you to class, both how to determine if a given point is a solution, as well as how to determine the actual solution or solutions given a picture of either a graph or a system of inequalities.